there are 4 options: 0, 1, 2, and 3. So number of subgroups of order 5 is at 12. So I hope all of the participants here know the answer, because all of them know the structure of the group is then the Lagrange's theorem also. What is Lagrange's theorem says? If we have a subgroup of a finite group, then its order divides the order of the group, right? If H is a subgroup of G, where G is finite, if G is a finite group, then order of H, or the cardinality of H, divides the cardinality of the group G. Order of H divides order. This is the theorem. And you know, Z12, this group is a cyclic group of order 12, and every subgroup of this is also cyclic. So that every subgroup is generated by some element in Z12. And every subgroup has order a divisor of 12. So this can see that there is no element having order 5, because 5 is not a divisor of 12. 5 not a divisor of 12. So it cannot have an element of order 5, so that it cannot have a subgroup of order 5 also. Okay, so that just Lagrange's theorem is helpful. Now the second question is about Lagrange's theorem. If I say, if the theorem says that if G is a subgroup of a finite group G, then it's any of its subgroup has order a divisor of the order of group. Okay, but the converse is not true. The converse of Lagrange's theorem is not true. That also is familiar to you all, and you may have counter examples. Okay, so we will come to this point in a later problem. Okay, so look at the second question. Is the question clear to you? All of you can read the question? Yes. Okay, thank you. Okay, second question is given as the matrices of the form by 2 matrices of the form SB01, where B can be any integer. S is plus or minus 1. This is the set. So this is a question asked in CSIR June session 2019. The options are, which of the following is or are true? This is the question. Okay, the options are, under addition, G is a group. What about this A? Under addition, can it be a group? It is easy to see that. See, S is plus or minus 1. So if we have a matrix with S1, B something else, whatever it B, and this is a member of G. And if we add that member to itself, its first entry will be true. Okay, the first entry is true. So that this cannot be a member of the group. It's easy to see that. Okay, it will not take much time to see this is not closed under addition. The set is not closed under addition. Okay, now the product G under multiplication, group multiplication, is an abelian group, is the second option. You can see that the product multiplication is closed. Any matrix of this form, if you multiply any 2 matrices of this form, it is again, the product is again a matrix of the same form, because here B can be any element. S is plus or minus 1, the 2-1th entry is 0, so you will get the first entry of the product is plus or minus 1. Okay, so this is closed, but you can see this is not abelian. For example, if you consider the matrix 1 0 0 1 4, and this is the identity matrix. So 1 1 0 1 into minus 1 1 0 1. What is its product? you can see that I am just computing the third one-tooth entry. The one-tooth entry will be 1 into 1, 1 into 1, 2. 1-tooth entry will be. Now, if we multiply in the reverse order, B into A, if this is A and second one is B, what is B into A? When you multiply B into A, what you are getting the second entry as minus 1 into 1 plus 1 into 1, that is 0. Okay, so these two are not equal. So this is not an abelian group. Okay, we will get group under multiplication. Its inverse is closed under inverse, closed under the multiplication operation. Because of this, S is plus or minus 1 and is 1 to 2 entry 0. Determinant is non-zero, so it's invertible. So inverse X, all properties you can verify. And associative law is true for, generally true for matrix multiplication. So that is also true. So it's a group, but not an abelian group. So here there is a point, abelian group. So this is also not right. Okay. So G plus is not a group. G dot is not an abelian group. Now every element in G is diagonalizable over C. What about that one? Diagonalizable means it's a linear algebraic concept. Diagonalizable means it is equivalent to some diagonal matrix. It's similar to some diagonal matrix. Okay, or we can say that the corresponding linear transformation has a form into a diagonal matrix. Okay, can be represented by a diagonal matrix in some basis of C2. Okay, now this is, you can see very directly by looking at the determinant of xi minus a. If a is a member of G, what is determinant of xi minus a? This is, it will be of the form. For example, if a is S is 1, if S is 1, you have x minus 1 minus b 0 x minus 1. Okay, so let me write down this on another slide. Okay, if we look at a, for example, if A is the matrix 1, 1, 0, 1, you see this is the end of G that satisfies all the conditions. First entry is 1, B is 1. We can be not getting. Okay. You cannot view my writings. Is it clear?
Yeah, it's clear.
Okay. So sometimes those who are watching in my mobile phone may feel some difficulty. So you can zoom out. Okay. So if this is the matrix you are selecting, what's the determinant of xi minus a? This is actually the characteristic polynomial of this matrix. And we could see that the characteristic polynomial is, in this case, x minus 1, 0, x minus 1. So the determinant is x minus 1 the whole square. Okay. And looking at the characteristic polynomial and minimal polynomial, we can find out its minimal polynomial. There are two choices for it, either x minus 1 itself or x minus 1 all square, because you know the relation between minimal polynomial and characteristic polynomial of a operator. I'm not going to the details of that. The minimal polynomial is a polynomial for which the operator t vanish, and this polynomial has the property, it's a polynomial of minimum degree, and it is a monic polynomial. And if you consider all polynomials that annihilate t, this polynomial will be a generator of that ideal. So all such properties are there. Okay, so I'm not going to the details of the linear algebraic properties of this. The only Cayley-Hamilton theorem you need here that says minimal polynomial and characteristic polynomial have same roots. And here the only root is 1, that is repeating 2 times. So the minimal polynomial has choice, either it is x minus 1 or x minus 1 all square. Now, if x minus 1 is the minimal polynomial, your matrix must be, that will give a minus I is equal to 0. If x minus I is the minimal polynomial, if we substitute for x is equal to the matrix A, A minus I will be 0. But this happens only when A is equal to I. And you can see that this is not the identity matrix. So minimal polynomial is not x minus 1. Minimal polynomial is x minus 1 whole square. But over C, it is diagonalizable. That is another result in linear algebra. It is diagonalizable if and only if its minimal polynomial is a product of linear polynomials. Here, the polynomial is not a linear polynomial. The polynomial is x square minus, x minus 1 the whole square. X minus 1 the whole square. It is not linear. So that it's not diagonalizable. This polynomial, this matrix, this you might have seen as an example in linear algebra. That's a non-diagonalizable matrix. So the option C also not true. Option C is also not true. Every element, some elements are there which are diagonalizable, but there are non-diagonalizable elements as well. Now, what about G? It is a group that verification I left as an exercise. It's a group under multiplication, and it is finitely generated because you can see that the elements like one is the identity 1 0 0 1. Another one is 1 1 0 1. This type of element will generate elements of the form 1b 0 1. Okay. Another one is 1 minus 1 0 1. This will generate elements of the, this is b is positive. Here b positive. This will generate elements of the form b 1 b 0 1, b negative. For negative b, this will. And if needed, we can include one more element minus 1 0 0. So minus 1 0 0. Okay. These elements are enough to generate this group. You can get every element in G as some power of these matrices or some combinations of these matrices. Okay, so that it is a finitely generated group is the correct option. For the second question, the answer is D. Okay, is it clear for all?
Yes.
Okay, that is just to check whether it is a group, and only the additional thing coming is whether it is finitely generated or not. Okay, then diagonalizable matrices also play a role there. So this is a question that appeared in CSIR June 2019. And these are a few questions I have selected for you. And these are also very simple one. Any finite cyclic group, you know, if any, infinite. Any infinite cyclic group, you consider, and you may know that any infinite cyclic group is isomorphic to Z. A lot of you may know this, or if you didn't notice this fact, you can notice it. And if you know this result, this question is nothing. Okay. Any infinite cyclic group, because a cyclic group is a group generated by a single element. And if it is infinite, so you can see that all the members of this, say, a to the power 0, a to the power 1, a to the power minus 1, etc., etc. Okay, these are the members. Never a raised to m equal to a raised to n happens if m not equal to n. This is not true in this case, if it is an infinite group. Okay, so that it will, there is a natural mapping, there is a natural isomorphism between this group and Z. You can map a raised to 0 to 0, a raised to 1 to 1. It's a natural association like this, and that will give an isomorphism. So any infinite cyclic group is isomorphic to Z. Then you can easily attempt this question. It is abelian, that is right. All its non-trivial subgroups are isomorphic to Z. This is another property of the group Z. You can see that any subgroup you take of Z, it will be isomorphic to itself. The group Z itself. Any subgroup is isomorphic to is the property of G. Isomorphic to G. G is isomorphic to G. Okay, even if it is a proper subgroup. Only the trivial subgroup is not isomorphic because only contains only the zero element, identity element. Okay? That is exempted here. So all its non-trivial subgroups are isomorphic to Z is right. As subgroups of any order. What about this question? Can anyone say? An infinite cyclic group. You can see it is Z itself. For Z, can we get subgroups of any order?
No, ma'am.
No. We will get only subgroups isomorphic to Z. For example, if you want to get a subgroup of order 10, it's not possible. Okay. Any finite number, you may not be able to find a subgroup there. Is isomorphic to Z is exactly the one that we have verified. Okay. Shall we go to the fourth question?
Yes, ma'am.
For any, okay, thank you. For any finite cyclic group G and for any integer m greater than 1, m dividing n, so m is a number greater than 1 divides m, which is true or which is not true. Okay, we can check all the 4 options whether it is true or not. G has a subgroup of order m. For any finite cyclic group G, for any divisor m of n, well, it's not equal to 1. G has a subgroup of. Can anyone say whether it's right or wrong? A. Option A. It's a finite. Yes. Hello. A finite cyclic group, and there is a divisor of the order of G, M. Can we say G has a subgroup of order M?
Ma'am, what is n?
Yes. I
What
didn't.
is n?
What is n? N is the
N.
order of G. Order of G. Dividing n. Yes. Sorry. Order of G.
False.
False. Why?
No, true, because G is finite cyclic group. So
Yes.
every divisor.
Yes, that is the point. It is finite and cyclic. As every infinite cyclic group is isomorphic to Z, every finite cyclic group is isomorphic to some Z. What is the order of that group? So if here the order is n, so it is isomorphic to Z. And this is true. A is not false, it is true. And this assures by the fundamental theorem of finitely generated abelian group. All of you know what is the fundamental theorem of finitely generated abelian group? This theorem gives the complete structure of every finitely generated abelian group. If you know the order of the group, you can see how many abelian groups are there of that order. Okay. So any finitely generated abelian group is isomorphic to a product of cyclic groups Zn and Z. So it is every group. If G is a finitely generated abelian group, you can find numbers, natural numbers n1, n2, etc. in R such that G is isomorphic to Zn1, Zn2, etc. Znr into some copies of Z if it is an infinite group. There may be, of course, some copies of Z also. Okay. So using these cyclic groups Z and Zn, we can classify all finitely generated abelian groups. And this number of copies of Z is known as the Betty number of that group. Number of copies of Z is known as the Betty number of the group. If D is finite, what happens? There is no copy of Z here. Only some ZNs will play role. Okay. So in this case, Betty number of finite groups are 0. There is no copy of Z. The number of copies is 0. So for a finite group, its Betty number is 0. Okay, that also we can relate from this fundamental theorem. Okay, this is the fundamental theorem. And this will ensure if your group has, if it is finite, I told you there is no copy of Z. So you will get some Zn1 into Zn2 into etc. Znr. You can find subgroups of any order dividing n1 in first copy, subgroup of order any divisor of n2 in the second group, and so on. So any divisor of the order of the group has a product like this. You can, if order of G is n1 into n2 into etc. nr, any divisor of order of G can be written as product P1 into etc. PR, where P1 divides N1, P2 divides N2, and so on, PR divides Nr. And you can find elements of that order in the respective groups and form a subgroup of order M. Okay, so fundamental theorem for finitely generated abelian group ensures. Most of the textbook gives the result itself. Every finitely generated abelian group, every finitely generated finite abelian group, or every finite abelian group has subgroups of order M for every divisor M of the order of G. That is true. Okay. Now, if G has a subgroup of order M, then it is unique. What about that? B.
This is true.
This is also true. So that's is that for a particular order, if M divides N, if for a particular M dividing, there is exactly one subgroup of that order. Okay, that is true for Zn. Not generally true. For example, if we look at S3, S3 has order of S3 is 6. Okay, 2 divide 6. You can see that there are 3 subgroups of order 2 in S3. One generated by the reflection mu1. If you know the standard notation, the group generated by mu1 reflections. Yes, S3 can be identified as a group of symmetries of a regular triangle, equilateral triangle. So what is the reflection? Reflection is you fix one of the vertices and interchange the other two. You flip the triangle, okay? You will get a symmetry there. So 2 and 3 are reflected. So that is mu1. And instead fixing 1, if you fix 2 and reflect 1 and 3, you will get the reflection mu2. And what is the group generated by mu2? It has order 2. Every reflection has order 2. So they will generate. Similarly, the one that fix 3 and 1 and 2 will generate a subgroup of order. That is mu3. The reflection is mu3. That also generates a subgroup of order 2. You can see that there are 3 subgroups of order 2. There is one subgroup of order 3, one subgroup of order 1, the trivial subgroup, and a group, the group, entire group S3 of order 6. Okay, the structure of S3, subgroup structure of S3 is that. So if M divides order of G, G has a subgroup of order M if G is a finite abelian group. If G is finite abelian group, the converse of Lagrange's theorem also true. Okay, converse for corresponding to every divisor of order of G, there is a subgroup. Okay, and this subgroup is unique. This subgroup is unique. Case Z. If G is Z. Okay, but for other groups that may not be true. That is one of the facts. Okay, so this is true if Zn, the group, because it is cyclic, it's isomorphic to Zn. So the second part, the second option is also true. G has an element of order M. Come on.
Yes, ma'am.
Yes, that's also true because every subgroup is cyclic. There are elements of order M. Subgroups of order M are generated by elements of order M. So all such, you can relate all these facts. If G has an element of order M, then it is unique. What about the option D?
It may not be. I think.
That may not be true because, for example, if M is 3, suppose you have the group which is its order is divisible by 3. Suppose n is a number which is divisible by 3. Then since it's a cyclic group, it is isomorphic to Zn, the group is Zn. You have a subgroup of order 3, say 0, A, B. And you can see that both A and B must have order 3. Their orders are 3 because 3 is a prime number. Okay, this itself is a group, it's a subgroup. So itself is a group, every element, its order divides the order of the group. The only divisor of 3 are 1 and 3. The order 1 is only for the identity. And for all other groups, all other elements, the order is 3. Okay, this is true for any group of prime order. If you consider ZP, all elements except identity. If A is not equal to identity, A has order P. Every element. So in ZP, there will be P minus 1 elements of order P. Okay, all elements except identity will have order P. Okay, so even if there is a unique subgroup of some particular order, and that subgroup is cyclic, the number of elements of that order need not be unique. So it depends on the order. If M is 2, then it is 1. Otherwise, for M greater than 2, that is not true. Okay. Actually, if order of, we can also find the relation. If order of G is some subgroup H is cyclic and its order is some K, it has phi of K generators. Okay, right? Phi of K is the number of primes less than number of elements relatively prime to K and less than or equal to K. Number of positive integers less than or equal to K and relatively prime to K. It's the Euler-Taussian function. That much generators are there, so that much elements of order M will be there. Okay, phi of M elements will be there. And phi of M is 1 only when M is 2. Okay, I think that question is over. All of you got what the ideas are conveyed. Okay, if you feel any kind of difficulty or any problem, if you already all if you want to skip it, just inform me. Or any change, if you need any change in my presentation, please free to be safe. You can freely contact or freely communicate with me. Okay, so go to the question 5. An abelian group of order PQ. Some mistakes are there. An abelian group of order PQ is cyclic if P and Q are primes. What about that option? Given it's an abelian group.
Yes, ma'am, it is true.
Cyclic if P and Q are primes. True or false? Both. Okay. It is false. If P is order of G is PQ and G is abelian. Our option is this. A. It is cyclic if P and Q are primes. is right or wrong?
Right.
False.
Right? False. It is false. Okay, right. So
Take S3. S3. Sorry, S3 is not available.
it's ZP into ZP. Right? This example will do the purpose. Right? It only says the product is PQ, P and Q are primes. If P and Q are same, what happens? It can be either ZP square or ZP into ZP because abelian. It is abelian only we are considering. So we have these are the two cases, but this is not cyclic. Okay. So option A is not right. Option A is false. Okay, it is not true. Then what about the option B? It's never cyclic. That you can avoid quickly. It is never cyclic. That never cyclic means it is not cyclic for any P for any Q. Can it be true?
No.
No, there are possibilities there. It can be cyclic because if is at P square in the previous example or is at PQ can happen that it is the group is at PQ. Okay, so it is never cyclic. That also not true. Okay. What about C? If P and Q are distinct primes, then it is cyclic. Option C is cyclic if P and Q are distinct primes. True or false? Distinct primes. Abelian group. By fundamental theorem, it is either ZP into ZQ or ZPQ. But if P and Q are distinct primes, they are co-prime. If P and Q are distinct primes, in this case, they don't have a common divisor other than 1. They are co-prime numbers. And so that this will be isomorphic to ZPQ. It will be cyclic. Right? Am I right?
Yes, ma'am.
Yes.
Okay. ZP into ZQ. If P and Q are distinct primes, because the group is abelian, only because the group is abelian. Otherwise, you have examples like S3 itself. S3 is a very good example for many of the concepts. Very good counter example. Okay. Many of the options you can discard using just looking at S3. Okay. S3, the order is product of 2 primes, 2 into 3. It's not abelian. Okay, but here the group is given to be abelian. So again, by fundamental theorem of finitely generated abelian group, its structure is, it has only 2 structures, but they are isomorphic in this particular case. But here, if P and Q are just primes, they need not be distinct or may be distinct. So in that case, there are possibilities. We can say either it is ZP into ZP or ZP square. So if it is ZP square, it is cyclic. Otherwise, it is not cyclic. Right?
Yes, yes. In first case, if maybe case, then it can be true. Maybe cyclic. Then if in first option,
Yes.
maybe cyclic word used, then can we say it is true?
Maybe cyclic, then it is true.
Thank you, ma'am.
It's a possibility. It can be cyclic or may not be cyclic. May be cyclic if the statement is like that. G may be cyclic or G may not be cyclic. Both are true. Okay, so let's go to the fourth option. Fourth option is cyclic if P and Q are relatively prime. Cyclic if P and Q are relatively prime. That is the option 4. P and Q are relatively prime means their only common divisor is 1. Here you can look at examples because the only fact is this order of G is the product PQ. P and Q are relatively prime. For example, you can think about S3 into some Z5. The order is 6 into 5. Order can be written as 6 into 5, okay? 6 and 5 are relatively prime numbers. But this group cannot be abelian because there is a non-abelian component, right? So if P and Q are relatively prime, this is the only statement, cyclic if P and Q are relatively prime, then it may not be true. But if we add relatively prime numbers, if P and Q are prime numbers, but they are relatively prime, in that case, this option is true. Got it? If P and Q are prime numbers and they are relatively prime, then the only possibility is the group is ZP into ZQ. Okay, otherwise, we have these kind of examples to contradict that. Okay, so C also not true. So only C is true, D also not true. P and Q are distinct primes, then it is cyclic, otherwise it is not cyclic. Okay, so let me go to the next question. So some statements are given. We have to check which of them are true. That is again based on the same concept. Okay, only in how many ways we can twist the same concept. Okay, that is the idea of asking questions in this kind of exams, competitive exams. Okay, in how many ways you can manipulate a situation. See, the first statement is every finite group of order n has a subgroup isomorphic to Zm for all m less than n. Every finite group of order n, finite group, given its order is n, subgroup isomorphic to Zm for all m less than n. See, very trivial case. For example, S3, if you take S3, even in abelian groups, you can see the situation. Order is n is 6. 5 is a number less than 6. 4 is a number less than 6. You cannot find subgroups of order 4 or 5 in Z6. So there are no subgroup isomorphic to Z4 or Z5. So this is not true in even if the group is abelian. For example, Z5. 4 is a number less than or equal to 5. Less than 5. Okay, you cannot find a subgroup of order 4 here. So we cannot find a Z4 inside Z5. So this is not true. You can easily discard that option. Every finite group of order n has subgroup isomorphic to Zm for all m dividing n. This is exactly the converse of Lagrange's theorem. Lagrange's theorem says if m divides the order of, if H is a subgroup of G, where G is finite, then order of H divides order of G. Divides order of G. This is Lagrange's theorem. H is a subgroup of a finite group G, and so on. But once we have a group of finite order and divisor of that element, that number n, we cannot ensure that there is a subgroup of order m. This is the converse of Lagrange's theorem, which is not true in general. which is not true. This is a very well-known result. Lagrange's theorem, its converse is not true in general. For example, you have the example A4. Its cardinality is, what is the order of A4? Order of A4 is actually the alternating group of 4 is 4.
12.
12. The order is 12. You can see that 6 divides the order. But A4 has no subgroup of order 6. This we can argue. A4 has no subgroup of order 6. Shall I prove this? Or if you need its proof? We can argue in many ways. One of the facts is this. If H is a subgroup of A4, order of H is equal to 6. Okay. A4 contains only even permutations. Okay. So H is 6. Then H must be isomorphic to S3. Can I conclude this? See, so all these are simple results. If H is a subgroup of A4, if there exists. Okay, if this is not true, we are going to argue that cannot exist. So if possible, there is a subgroup of order 6 in A4. What happens? This must be isomorphic to S3 because A4 cannot contain an element of order 6. So it cannot be cyclic. H cannot be cyclic. It is not cyclic because cyclic means I got order 6 group. Cyclic means it must have an element of order 6. A4 cannot have an element of order 6. S4 cannot have an element of order 6. So that it cannot be cyclic. So that it is a non-cyclic group of order 6. Only two groups are there of order 6. One is cyclic and the other one is non-cyclic, non-abelian group. These are the only two groups of order 6 up to isomorphism. Okay, so it cannot be isomorphic to Z6, so that it should be isomorphic to S3. And you know, S3 has 3 elements of order 2. S3 has 3 elements of order 2. We have already verified it. The reflections, 3 reflections. So that here also H has 3 elements of order 2. Now in S4, what are the elements of order 2? The partition has the form, if it is a transposition into C into D into E, sorry, S4. C into D, only 4 characters are there, CD. Or AB into CD. This kind of permutations only will give order 4. But this is not an even permutation, it's an odd permutation. So this kind of permutations are not in A4. So, but this is an even permutation. So this kind of permutations are in A4. So what are the permutations of this type? You can see that 1, 2 into 3, 4. 1, 3 into 2, 4. And 1, 4 into 2, 3. These are the 3 permutations of this type. Okay, this type permutation. Only 3 permutations are there in A4. So all the 3 members are in H. They are all members of H because H is isomorphic to S3, must contain 3 members of order 2. So only 3 members are there in A4 of order 2. They are all elements of H. But you can see that these 3 elements together with identity will form a group. What is the order of this group? If K is the group containing the 3 members, the 3 elements of order 2 and the identity, order of K is equal to 4. It's a group, subgroup of A4 of order 4 and subgroup of H of order 4. But H has order 6, 4 does not divide 6, so it cannot happen. Okay? So this is one way we can argue A4 cannot contain a subgroup isomorphic to a subgroup of order 6. You got it?
Yes, ma'am.
Okay, so let's go to the question again. So Lagrange's theorem, converse is not true in general. And so every finite group of order n has a subgroup isomorphic to Zm for all m dividing n. Isomorphic to Zn, even there may not exist a subgroup of that order m. Okay, that we have proved. For example, you can take A4 and the divisor m you can take as 6. Okay, so this counterexample will prove this is not true. B is also not true. Every infinite group has a subgroup isomorphic to Z. Yes, I think that will need a detailed discussion. What you feel, whether it is right or wrong, you have encountered such a problem earlier?
No, ma'am.
Okay, so I will discuss it in another later. Another problem is related to this question. So I will explain the situation. Because this is in one of the factor groups will provide a counter example here. Okay, so we will discuss it later. Anyway, this is not true. The last question, I think, last but one question is this. We may discuss the details there. Okay, what about the fourth one? Every infinite group has either a subgroup isomorphic to Z or a subgroup isomorphic to Z. Yes. Option C was every infinite group must have a subgroup isomorphic to Z. That is wrong. Okay, we just accepted that result. Now see this, either a subgroup isomorphic to Z or a subgroup isomorphic to some Zn. What do you think? This is true because the group is infinite. Okay, so there are elements other than identity. Okay, so there is an element other than identity. If you look at the group generated by A, it will be a cyclic group because it's generated by a single element. Okay, we are constructing like that. Either it will be finite or infinite. Only two choices. Either it will be finite, as it is not the identity element, its order must have at least two. Okay, so either it is a finite cyclic group or it's an infinite cyclic group. That if it is a finite cyclic group, it is isomorphic to some Zn. Or if it is not finite, all the a raised to n's are different, you will get the group isomorphic to Z. Okay, so you should get a subgroup, or you just take an element other than identity. What is the subgroup generated by it? Either it will be isomorphic to Z or it will be isomorphic to Zn for something. So the option D is right. Okay. Is that or is it? Depends, because whether a raised n's terminate at some stage or whether it continues to be different, to give different elements. Okay. Am I right?
Yes, ma'am.
Okay. Then look at the next question. It's a question appeared in GATE exam for 2018. A group of order 12 has a non-trivial proper normal subgroup. Need not have a non-trivial proper normal subgroup, has an element of order 6, has a subgroup of order 6. So immediately you can drop the two options C and D. We have already verified A4 is a group of order 12. It cannot have a subgroup of order 6, and so that it cannot have an element of order 6. Okay. The part A and B, options A and B need some explanations. It has non-trivial proper normal subgroup or need not have non-trivial proper normal subgroup. The two are related. Okay. So, what is the question number? 7. Okay. Order of G is 12. Okay. So order of G is 12. So here I think we require silo theory. The silo theory part. 12 is 3 into 4. That is 2 square root 3. Okay. So prime factorization of 2 times. Okay. Then it has two kinds of silo P subgroups. The 2 silo subgroup. I think you know the idea of silo subgroups. If anyone don't know what is a silo subgroup, please either raise your hands or okay. Janvi has raised hand. That means you are not familiar with the concept of silo theory.
Yes, ma'am.
Okay, I will explain this. Silo to silo subgroup. Silo group is an you need to speak. Okay, so you can see that if any finite order, so suppose G has a finite order, say n, okay, every natural number other than 1, minus 1, 0, it has a factorization into prime numbers, okay, p1 raised to n1, etc., some pk raised to nk, okay. Anyway, it must, n is a number not equal to 1, it must have a prime factor, okay. So you can write n is equal to some p raised to k into some m into it. You can write if it has some prime factor, how many times it is repeating, where m does not contain a p factor. Okay, in this way you can express. And the first silo theory says that the converse of Lagrange's theorem, there is a special situations where the converse is true. If your divisor is a prime number or prime power, the group has subgroups of that. Okay, I have to explain it in detail. The converse of Lagrange's theorem, we have seen that if m divides order of G, that G need not have need not have a subgroup of order m. Similarly, need not have an element of order m. This is the general statement of converse, and this is not converse. Lagrange's theorem says if every subgroup has order dividing the order of the group. But the converse is not true in general. The converse is true if the divisor m dividing n, if m is a prime number, then converse is true. That means there is a subgroup of order p. If the divisor you are considering is a prime number, the converse is true. That means the group G has a subgroup of order p. If p is a prime, okay, m is a prime number. And not only for primes, prime powers also. If m divides n and m is a power of p, then also G has a subgroup of order p. This result is called the Cauchy's theorem. And this is also a part of the first silo theorem. These two are parts of first silo theorem. There are 3 silo theorems in general. And one more fact there is, every group of order p raised to I minus 1 is normally group of order p raised to I. That is a part of the first silo theorem. Okay, we are not going to that side. Okay. See, now silo groups are, so as I mentioned, so if n is written as p raised to r into m, where P does not divide M, R is greater than or equal to 1. That means P is a prime number dividing N. And the prime number may appear more times. Okay, more than one times in N as a factor. Okay, that happens. Maybe P square divide N, but P cube does not divide N. So R is 2. Okay, in that case. Then, so this has subgroups of order P, P square up to P raised to R. Okay, it has. Now, what is the subgroup of order P raised to R? The maximum power of P that divide N. Okay, any subgroup of that order is called a silo P subgroup. This is one way we can define, or P silo subgroup. Both are using P silo subgroup or silo P subgroup. It's a feeling. So, what is the maximum power of the prime P dividing the order of the group? The group has a subgroup of that order, P raised to R. That is a maximal groups in which every element has order P, P or power of P. In general, silo groups are there. So we say that a group G, finite group G, it is finite, is a silo group if every element in G has order a power of P, P raised to R for some positive number R. Okay, every element, just Z8, its order is 8. So the divisors are 1, 2, 2 square, and 2 cube. Elements of order 1, 2, 2 square, 2 cube. So every element is a power. Every element has order a power of 2. So it's a silo. Such groups are called silo. This is a silo 2 group. It's a silo 2 or 2 silo group. This is a 2 silo group if the P is equal to 2. In general, it is a P silo group. G is a P silo group if every element in G has order some power of 2. That's the only thing. This is general definition of silo group. And when we come to any group and silo subgroups, the subgroup has this property. Every element of that subgroup has this property. So silo 2 subgroups are every element of the subgroup of G has the property, every element has order power of 2. Okay. Now such maximal subgroups. Okay, see here Z8 has a subgroup of order 4. Okay, and for this subgroup also every element has order a power of 2. So in Z8 this is also a P silo group, 2 silo group. But what is the maximal 2 silo group? That is Z8 itself. Okay, and maximal 2 groups are called silo. Maximal means that is why we use silo. Okay, once again so P group and P silo group. I think P group, every order has a power of P. P silo group means such maximal P groups. In silo groups are considered inside a graph, okay, and inside a group. So in a group, what are the maximum? For example, if I take S6, okay, S6, its order is 6 and that is 2 into 3. So the maximum power of 2 is 2 raised to 1. It has 3 groups of order 2, H1, H2, H3. And the maximum power of 2 is 2 raised to 1, it is 2. So all these 3 are 2 silo subgroups of S3. S3. And there is one silo 3 subgroup. The silo 3 subgroup, every element has power of 3 as order. And only power 3 raised to 1. Okay, no higher power divides order of 6. So a group of order 3 will be the maximum. Okay, now if you look at a group Z12, 12 is 2 square into 3. So 2 silo subgroup has order 4 because the maximum power of 2 dividing 12 is 4. 3 silo subgroup has order 3 only. Okay. If the group has p raised to 10 into q order, the p silo subgroup has order p raised to 10. Q silo subgroup has order q. If q is prime, p and q are primes. Okay. So for prime powers, there exists subgroups. Such subgroups exist. That is ensured by first silo theorem and converse of Lagrange's theorem true. So that gives such groups exist and they are called silo groups. So they are maximal P. Okay, you got it? I hope
Yes, ma'am.
Janvi got a very broad idea about P group. P groups and P silos subgroups are the maximal P groups of a group. Okay. Anyway, so I think in this case, in this problem, we need that non-trivial normals to look at the subgroups of a group of order 12. Our question is this: order of G is 12, and the question is this: whether it has a non-trivial normal subgroup. Whether it has or need not have. That there are two non-trivial, proper normal subgroup. Has or need not have. Proper. Now 12 is 2 square into 3. Okay. So it has two silo 2 subgroup. Okay. 2 silo subgroups are there and 3 silo subgroups are there. Okay. In silo 2 subgroups has order. What is the order of that such group? We can call it say H1. The order of this group is 4 and here the order is 3. Okay. Another theorem, the second silo theorem says that any two silo groups are conjugates. If P1 and P2 are two silo groups, then P1 is equal to G into P2 into G inverse for some G in G. P1 and P2 are silo.
Ma'am, screen is not working.
Not visible.
Now visible.
Is it okay? Is it visible now?
Yes, ma'am. Yes,
Okay.
yes ma'am.
So if P1 and P2 are two subgroups, two silo P subgroups of a group G. In a group G, then they are conjugates. That means one of them can be obtained as a conjugate of the other. This is the second silo theorem. See, there are 3 silo theorems, basically. This is the second silo theorem. For showing there is a normal subgroups, etc., we use this kind of, this theory, mainly used that. And there is third one. Third one is third silo theorem. That is more related to this kind of arguments. Whether what is the number of such regarding the number of silo subgroups. Okay, third theorem says that if we have P divides the order of a group P is a prime number, then it has silo P subgroup. Okay, the number of silo P subgroups if this number is an integer which is congruent to one modulo P. That means if this number of silo P subgroups is some K, this K minus 1 is divisible by P. Also, this number divides order of the group. So, for which group we are considering, the order of G is N, okay, and P divides N. It has silo P subgroup, P silo subgroup. And how many such subgroups are there? So, the answer of that question, giving some information regarding the number of silo subgroups. That number is a divisor of order of G and that should be congruent to one model. That means it's minus 1 is divisible by p. So using this idea, you can see that if we count the number of 2 silo subgroups in a group of order 12, what is this number? It should be congruent to 1 modulo 2 and divides order of G, that is 12. It is a divisor of 12. The divisors of 12 are 1, 2, 2 square, 3, and 4, 6, 12. Right? Okay. So among these numbers, what are the numbers congruent to 1 mod 2 and dividing 12 are there? What are the numbers congruent to 1 mod 2? Only 1 and 3. Okay. So there are either 1 silo 2 subgroup or 2 silo 2 subgroups. Not 2, 3. Number of silo 2 subgroups either 1 or 3. So either 1 or 3 silo 2 subgroups are there. That means either 1 or 3 subgroups of order 4 are there. Similarly, if we look at the silo 3 subgroup, its number, what is it? It is congruent to 1 modulo 3 and divides order of G. So among these numbers, what are the numbers congruent to 1 modulo 3? They are only 1 or 4. So we have either 1 or 4 silo 3 subgroups. Okay. Now suppose there are 4 silo 3 subgroups. Silo 3 subgroup has order 3. Okay. 3, power of 3, highest power of 3 in 12 is 3. So 3, there are 4 subgroups of order 3. Okay. If H1 and H2 are 2 subgroups of order 3, they have only one element in common, the identity. Okay. Because order 3, every other element has order 3. So if A is an element in H1, which is not the identity, and if that is in H2, both the groups will be same. Okay. If there are 4 subgroups of order 3, they will be different for them. So that these 4 subgroups will have 8 elements of order 2. 8 elements of order 2 plus identity. There are total 9 elements in these 4 subgroups. Now only 3 elements left in a group of order 12. Okay. So there cannot be 3 silo 3 subgroups, because in a silo 3 subgroup, silo 3 subgroups we are considered. This order is 3. Silo 2 subgroups. Okay. We have if 4 silo 3 subgroups are there. There are 8 elements already we have listed along with identity. There are 8 two ordered elements. And now if there is a subgroup of order 4, there is 3 more additional elements will get. But if there are 2 silo subgroups, 1 or 4, okay, silo subgroups, number of 2 silo subgroups is 1 or 3. This is if 3 silo 2 subgroups are there, what happens? We will get more than 4 elements from that 3 subgroups. Okay, but that is not possible because we have already listed 9 elements here. Only 3 elements left in. So only 1 silo. So what we can conclude is this: if G has order 12, then G has either exactly 1 silo 2 silo subgroup or exactly 1 3 silo subgroup. The possibilities, one of the cases 1 or 4, one of the cases 1 or 3. 4 silo P subgroups of 1P and 3 silo P subgroups of 1P will yield greater than 12 elements. Okay, so that together cannot happen. So at least one of them must be 1. Either the number of silo subgroups is 1 or the number of silo 3 subgroups is 1. Okay, so one of them must be 1. If there is only one silo P group, by the second isomorphism theorem, the conjugate of that group must be itself. That means it is a normal subgroup in the group. This is for every G in G. For each G in G, you form the conjugate GP inverse. And P is the only silo group. Means P is the only group of that order, subgroup. So every conjugate must be same as P. Because conjugate also have the same structure, same cardinality, just like P. Okay, only one group of that cardinality. So the PG inverse must be equal to P. And this is true for every G, and that case P is a normal subgroup. So what we have is, in a group of order 12, either there is a normal subgroup of order 4 or a normal subgroup of order 3. That is right, using silo theory. Okay, and you can also find more arguments without using silo theory, or using some other concepts, we can find the result. So what is the conclusion? The question 7 has a non-trivial proper normal subgroup is true, need not have, it's not right. Okay, always it should have a normal subgroups. Okay, so to find normal subgroups, we can use silo theory in all aspects, in all dimensions, on all directions also. You can apply this. Okay, if you thoroughly know what is silo theory, so in many such questions you can use it. There may be other concepts also we can use in this particular situation. So I would like to say what is silo theory. That is why I selected this method. Okay, I hope you can enjoy and can follow. If you feel any problem, please inform me. Please stop me, and then we can discuss that. Okay, let's continue.
Yes, ma'am.
Yes, ma'am.
Okay. So this question we have discussed, question 7. As already mentioned, it is a question for a GATE 2018. 2018 GATE. Okay. Now, question 8 is regarding number of distinct subgroups of Z99. So this also already we have discussed the theory that can be used in this case. That is, for Zn, this is Z99. Okay. This regarding Z999, not 99, 999. So for Zn, the structure, this group is cyclic and every subgroup is cyclic. And for every m dividing n, there are subgroups and they are cyclic. Okay, so all these facts we have considered. Number of distinct subgroups. So for Zn, corresponding to every divisor, there is a subgroup, means we have to consider distinct divisors. Okay, what are the divisors of Zn? This is only the question regarding it. What are the different divisors of 999? 999, you can see that it is 9 into 111. 9 is 3 square. 111 is 3 into 37, right? 111, it is 3 into 37. Okay, so ultimately the factorization, prime factorization is fundamental theorem of arithmetic. 37 is a number, so this is the prime factorization of 999. So what are the roots? 1, 3, not 3 square, 3 3s. Okay. 1, 3, 3 square, 3 cube. Okay. And 37. So 1 in the numbers are 1, 3, 3 square, 3 cube, 37. 3 into 37, 3 square into 37, and 3 cube into 37. Okay, these are the distinct 1, 2, 3, 4, 5, 6, 7, 8. These are the distinct divisors of 999. And for Zn, for each divisor there is a subgroup, and the subgroups are unique. Corresponding to every divisor, there is a unique subgroup of that order. So that gives, corresponding to each of these devices, we get a unique subgroup. So there are exactly 8 subgroups of. So this is the answer. 8 distinct devices are there. So 8 distinct subgroups are there. Okay. See, JAM 2022 question. Okay, I hope it's fine. So number of cyclic subgroups of the quaternion group of order 8. Only mention about the group, quaternion group of order 8 is Q8. You can describe the group in many ways. One of the ways is this. It contains 8 members, can be written as plus or minus 1, plus or minus I, plus or minus J, plus or minus K, in such a way that with 1 and minus 1 multiplication, kind of multiplication we are using the operation. 1 and minus 1 are just multiplied as the in the general situation. For I into I is taken as minus 1, J into J is taken as minus 1, and K into K is taken as minus 1. I square, J square, K square. Now, if you multiply I with J, you will get K. J with K, you will get I. K with I, you will get J. In that cycle, I, J, K. This is the cycle. I with J, if you multiply, you will get the third element. J with K, if you multiply, you get the next element. In this order. But if you reverse the order, J into I, you get minus K. Just like cross product of unit vectors, IJK. Okay? Just like that. So this is the way we define this group. This is the group of quaternions. And I know many of you know this group. Okay. How many subgroups, cyclic subgroups are there for this group? Only we have to look at the groups generated by all these members. What are the groups generated by all these members? That will give the number of number of cyclic subgroups. So 1 generate the group 1 itself, minus 1 generate the group minus 1, and minus 1 square is 1. So you will get 2 element group. If you consider I, what is the group generated by I? It will be I square, I cube, etc. And I square is minus 1, I cube is therefore minus I, and I raised to 4 becomes 1. Identity. Okay. So similarly, J generate a group of order 4, and K generate a group of order 4, like similar. 1 minus 1 and K minus K, 1 minus 1 and J minus K. There's are. Now, all the 8 elements we have considered. If we choose minus I, what to get? Minus I square is again minus 1, minus I cube is minus I. Minus I cube is, plus I, and minus I raised to 4. So you will get the same one. So I and J generate the same, minus J and minus J generate the same group. K and minus K generate the same group. So we get how many cyclic groups are there? We have only 1, 2, 3, 4, 5. The answer is 5. In this case, okay, we have discussed the question 9. Yes. Now let's go to question 10. Number of elements of order 15 in is 60 into Z50. Okay, again the structure of group is playing a role, and the subgroups, any subgroups of any order, that groups are unique. Such ideas will help. Okay, just consider Z60, Z50 separately. For 60, the factorization is 6 into 10, that is 2 into 3 into 2 into 5, 2 square into 3 into 5. And 50 is 5 into 10, that is 2 into 5 square, 50. Okay. These are the factorization. Now, in a product group, G into H, if G and H are, sorry, Zm into Zn. If we have an element in G and an element in H, A and B respectively, the pair AB, its order is, what is the order of A in G? What is the order of B in H? Their LCM is the order of this pair AB, okay, in G cross H. Okay, this you know, the order of an element in the product of two groups or more groups. You can generalize. If you have the order of A in G, this is the order in G, and this is the order in X, order B in H. Similar. So, in order to get an element of order 15, because every subgroup, such an element will generate a subgroup of order 15. We have to get the LCM of order of some element in Z60 having order some number in Z60, just write 60 here, comma, order of some element in Z50, their orders have LCM equal to 50. When this happens, which elements have LCM 15 here? So this is possible. Suppose you have 15, because 15 is a factor here. Here we don't have 15, only 5 you have here. So this happens. An element of order 15 in first group and element of order 1 or 5 in second group. Okay. If we have order of A is equal to 15 and here order of B is 1 or 5, in both cases what we have LCM is equal to 50. Okay. This is one choice, either 1 or 5. You can choose orders. We are considering only orders. Now another choice you are giving is the order 3 elements, or an element of order 3 from Z60 and an element of order 5 from Z50. So these are the not 4, 15 with 1, 15 with 5, 3 with the 5. So how many elements of order 15 are there in Z60? In Z60, number of elements of order, number of A such that order of A is equal to 15. It is the 15, every such element generate a group of order 15. Okay. So only one group of order 15 means all such elements belong to some particular group. All such A belongs to some particular group of order 15. So this is actually, how many A's are there is actually the number of generators of a group of order 15. So this is exactly phi of 15. And phi of 15 can compute it as 8. Okay. Number of generators of a group of order 15 is 8. So there are 8 elements of order 15 in 60. The number of elements of order 1 in any group is the identity alone. Now, how many elements of order 5 are there in Z50? Again, 5. The number of generators of a group of order 5, that is 4. Okay. So, number of elements of order. So, here you have, here there is only one element of this order. Here there are 4 elements of 5 order. Here we have 8 elements of order 15 and 2 elements of order 3. Same argument. Order 3, a group of order 3 has 2 generators. So only 2 elements are there of order 3. So what we have, the number of combinations, and 15 and 1, such elements are 8 into 1. 15 and 5, 8 into 5. 3 and 5, 2 into 8 into 5.
Ma'am,
5 or
it should be 18 to 4.
yes, right. 8 into 4, yes, right. And 2 into
And
4.
15 and 3 is also a possibility, right?
3 is not in Z50. We cannot find an element of order 3 in Z50.
Oh, okay, ma'am. Okay.
3, there are elements of order 3 in Z60 that we have considered. Okay, right? So 8 into 1, 8 plus 8 into 4, 32 plus 2 into 4, 8. So that total 8, 40, 48. So the answer is 48 here. Okay, so for this question, answer is 48. Okay, so just compute the number of elements. So in Zn, it is easy to compute because unique group of that order. Okay? So the number of elements of a particular order is exactly the Euler-Torsion function. What is the value of that number under the Torsion function? Okay, 5. But in general case, that cannot be that much easy to find how many elements are there of a particular order. But in Zn, all things are under our control, okay? Because we have a complete structure of the groups Zn, and very simple structure for that. Okay, question 11. It's already 12. I think we can go up to 12:30. Vinod, are you here?
Yeah, yes, miss.
Okay, 12:30. Okay, question number 11, you can easily answer. Number of elements of order 3 in S6. Actually, there is a formula to find it. Okay, in Sn, all these questions are can be answered using this formula. So in Sn, we have is Sn has permutation. Okay, 1, 2. It's a permutation group of 1, 2, etc. n. Okay, some sigma 1. If sigma is the permutation, sigma 2, etc. Sigma something. And this every element in Sn can be written as a product of cycles, disjoint cycles. Every element can be written as a product of disjoint cycles. So for a particular element sigma in Sn has a product of disjoint cycles. Suppose there is one cycle, it is 1, 2, 3, 4, 5, 6. Okay, so there are cycles of same length. So you just write down the structure of sigma like this: L1 raised to N1, L2 raised to N2, etc. L some R raised to NR. This means there are sigma is we can write sigma is equal to, but sigma is this, just mention that sigma is a product of N1 cycles of length L1, N1 cycles of length L1, N2 cycles of length L2, and so on, NR cycles of length L1. This is known as the structure of it. So just write down as a product of cycles, disjoint cycles, and you consider cycles of same length together. How many cycles of length 2 are there? How many cycles of length 3 are there? And so on. Okay. So if we write sigma like this, you can see that the number of elements of this structure or elements in Sn having this structure can be computed using the formula n factorial divided by L1 raised to N1 into L2 raised to N2 into etc. LR raised to NR into N1 factorial into etc. NR factorial. The number of elements having the structure, this structure is counted using this formula. So if you know the formula, it is easy to find structures, find the elements of this structure, this particular structure. Okay, I think all of you got the idea.
Ma'am, can you explain this with an example?
We will come to examples. These questions are based on this. So we will explain these examples like this. Okay. I hope this formula you got. Okay, number of elements of order 3 in S6. Let us get this question. That is the question number 11. Number of elements of order 3 in S6. So our group is S6. Okay. So in S6, the structure of a permutation, if sigma is in S6, structure can be, sigma can be the identity element. That identity element has structure 1, 2, etc. 6. Okay. This is the product structure. Okay. All cycles of length 1 only. Okay. So this cycle has length 1. 1 raised to 6 is the structure of sigma. Okay. Now, if sigma has this, so a transposition, say 1, 2, and 3, 4, 5, 6, just like this. So, what is the structure of this sigma? A cycle of length 2. So, length 2, number of cycles 1. Length 4, number of cycles 1. This is the structure. Okay, like this. Okay, so we have to find order 3, the structures giving order 3. Suppose you have a cycle. This cycle, what is the order of sigma? If this
Ma'am,
is your
are you
sigma,
writing something?
yes,
The
you
screen
can.
is freeze.
Screen not visible.
Screen is freeze.
What about now?
Oh, now visible.
So, okay. Suppose this is your sigma, the product of cycle 1, 2, and 3, 4, 5, 6. Okay. For this cycle, what is the order of sigma? What is its order? The cycle, it's a first cycle has order 2. Second cycle has order 4. We have to consider the LCM. Okay, the product will be its sigma raised to n will be identity if n is a common multiple of both orders of these two cycles. Okay, and least such common multiple will give the order of that element. Okay, LCM of 2n. Okay, so in these structures, so what are the possible structures of elements in S6? One is this identity element, 2 and 3. There are 3 cycles into 3 cycles like this, D, E, F. 2 cycle into a 4 cycle, 3 cycle into 3 cycle, a 3 cycle into 1 cycle, 1 cycle, 1 cycle. Okay, that also. So only among all the structures, only these 2 kind of structures will give order 3, right? Any other structure, for example, 2 cycle into 4 cycle. What is the LCM? It is 4. So order will be 4. For this particular element, its order is 4. Okay, but we want to get an element of order 3. So either it will be a product of 1 3 cycle together with 1 cycles, or 2 3 cycles also will give, because the LCM of 3 and 3 is again 3 order 3. So only these kind of structures will give. So our sigma, if it is an element of order 3, sigma will have a structure like this or this. Okay. Now what is the number of elements having this structure? That is 6 factorial. N is 6 here. 6 factorial divided by, what is the structure here? 3 raised to 1 and 1 raised to 3, right? 3 raised to 1 and 1 raised to 1 cycle of order 3, 3 cycles
Yes,
of order. Yes. Into, we have to multiply the 1 factorial and 3 factorial 1. Okay. L1 raised to N1, L2 raised to N2. N1 factorial into N2 factorial. Okay. So this kind of elements, its number is this. Similarly, there are elements of this type, 3 raised to 2. Structure is 2 cycles of length 3. Okay. So such elements are 6 factorial divided by 3 square into 2 factorial. Okay. 3 square into 2 factorial, both are same. Okay. So what is the result? Here you have 1 into 1 to 6, 1 into 2, etc. to 6. There 3 factorial get cancelled. So 4 into 5 into 6 and 3 get cancelled. So 4 into 5 into 2. What you are getting is 40 for the first term. And for the second term also you are getting 40. So there are 80 elements of these two structures. Okay. So these are the only structures giving order 3 in S6. I hope the formula is also thorough.
Yes, ma'am.
So the answer is 40. In this situation, the answer is 40. Okay, the second question is the same type of question. Or number of elements of order 8 in S6. And that is easier than, because in S6, when you get order of an element is sigma, order of sigma. Suppose sigma is an element, order is 8. What are the partitions giving 8? 6,
8, 1.
8, but S6, we are considering
Sorry.
S6, only 6 characters. 8, 1, 4, 2, such will give. So integer partition, you can see that 8, when you look at 8, 8 plus 0, and that is 8, 4, 4 plus 4. Okay, that integer partitions are there. But in S6, what you will get? Either 1 plus 5, 2 plus 4, 3 plus 3, like this. Okay, then 5 can be split into 1 plus 1 plus 1, like that. 2 plus. But the only thing, when any factorization, any such partition will not give the LCM is equal to 8. LCM is equal to 8. For getting LCM is equal to 8, what should be your product? What should be the structure of that? 2 and 4 will not give 8, only give 4. Okay, so there is no such elements in S6. Even though 8 is divisor of 6 factorial, there is no element of order 8 in S6. Okay, same. You can go through various structures in S6. You can see that no structure will give order 8. Okay, so the answer is 0 here in this case. And number of elements of order 12 in S7. S7, 12 is possible with the, what is the situation when 3 and 4. Cycle of length 3, cycle of length 4. Okay, that's the situation because it is in S7. So A, B, C into D, E, F, G. This kind of a, no other structure will give LCM 12. 3, here order is 3, order 4, 3 and 4 will give LCM 12. Okay, this kind of. So how many elements are there having this structure? That is 7 factorial divided by. So cycle of length 3 is 1. Cycle of length 4 is 1. So this 3 raised to 1 into 4 raised to 1 into 1 factorial. 1 factorial. So 3 into 4 get cancelled in 7 factorial. You are getting 420. 420. Multiply this, you will get 420 is the answer. So number of elements of order 12 is 420 in S7. This is also taken from JAM 2022. Last year JAM exam. Okay. Now number of 4 cycles in, this is cycles only. 4 cycles. So A, B, C, D, this form, any cycle of this form. So there are 7 characters. So A has 7 choices, B has 6 choices, C has 5 choices, and D has 4 choices. Okay. So using this, you can compute how many cycles, 4 cycles are there. Okay. Or you can use the structure formula. This is a 4 raised to 1. 4 raised to 1. So 7 factorial divided by 4 raised to 1 into 1 factorial. So that also will give. Okay, so I hope that idea. So there is another relation in the same nature. The sigma I have given is just a 1, 2, 3, 4, 5, and 2, 3, 1, 5, 4. This is sigma. Okay? And what is n sigma? Those elements in S5 which commute with the sigma. So set of all tau in S5 such that sigma tau is equal to tau sigma. This is the question. So now if again the same, if sigma has a structure like this, L1 raised to N1 into L2 raised to N2, etc., LR raised to NR, the number of elements having this structure is that we have seen that number of elements with the structure sigma is n factorial divided by L1 into N1, etc., LR into NR into N1 factorial into etc., NR factorial. This we have seen. Okay. Another thing is the number of elements commute with any element having this structure. Suppose sigma is an element having this structure, then number of elements commute with sigma is exactly n factorial. This is L1 raised to N1 into L2 raised to N2 into etc. LR raised to NR into N. What is the denominator of this one? That is exactly N1 factorial into etc. NR factorial. Okay. If we want to compute the number of elements which commute with an element having this structure, this is just this number. Okay. So in this case, what is the structure of this cycle, this permutation? 1 goes to 3, 1 goes to 2, 2 goes to 3, and 3 goes to 1. Okay. Into 4 and 5 commute each other, interchange. So this has structure 4 raised to 1 into 2 raised to 1. Okay. 4 raised to 1 into 2 raised to 1. Sorry. 1, 2, I repeated. 3 raised into 2 raised to 1, right? The structure is 3 raised to 1 into 2. So if we apply on this formula, 3 raised to 1 into 2 raised to 1 into 1 factorial into 1 factorial. This is the answer. Okay. So what is it? 3 into 2, that is 6. There are 6 elements that commute with the sigma. That is the number of elements of n sigma is 6 is the answer. Okay. So what is the number of elements having structure equivalent to sigma is n factorial divided by this number. But the denominator alone will give the number of elements commute with the sigma. Okay. Now, which is false on S5? 16. I think I will skip this question because the same kind of arguments we have to use there. So I skip the question 16. I have to. Yes, the question 17. I think it is given that G is a non-cyclic group of order 57. Order is 57. The 57, its factorization is 3 into 90. Okay, these are the prime numbers. And it is a non-cyclic graph. So it is not abelian. Exactly one subgroup of order 90. That is H. So H is a subgroup of G. It has order 90. Only one subgroup of order 19. Okay. Now say for every G in G which is not in H, what is the order of G? This is the question. Okay. If you consider an element of G which is not in H, what is its order? Okay. The order of an element in G may be 1, 3, 4, 19. And it is not cyclic, so that it cannot be 3 into 19. So the possible order of elements are either one gives only for identity, maybe 3 or 19. Okay. Now, only one subgroup of order 19 is given. Okay. So, If we choose an element which is not in H, an element of G, can order of G is equal to 19? Can this happen? If order of G is 19, what happens? That generates a group of order 19, and that will be H itself. Okay, but G is not an element of H because only one group of order 19. So this should be equal to H. So it cannot be equal to 90. So what is the possibility? The only possibility is 3. So for every G not in H, order of G is 3. This is the answer. Okay. This question, this is in JAM 2020 asked. Now 18 also, it's taken from GATE 2020. It's again regarding the, but here we have to argue that using Silo theory that there is exactly one subgroup of order 90. Actually, that is true. In this question, that is given, but here we have to argue that also. Then only, if you know this, such a group has exactly one, because by looking at the Silo 3 subgroups and Silo 90 subgroups, you can argue that the only divisor of 57, which is congruent to 1 modulo 3 is 19 or 1, and only number divisor of 57 that congruent to 1 modulo 19 is 1 only. Okay, only one subgroup of 19 is there. Okay, using Silo theory. Okay, so that identification is good here. So number of elements of order will be all other elements. So 19 order elements are 18. An element identity has order all other elements. So how many elements are there? 57 minus 19 elements are there. It is 38. Yes. There are 38 elements of order 3. The second question, question 18 was that. What is the number of elements of order 3? That is 38. Okay. So all elements, all the 57 elements, 18 have order 19, one identity has order 1, and the remaining 38 elements have order 3. Okay. These two questions asked in 2 of the important exams in 2020. Number of homomorphisms from A5 to S4. This you may have some formulas to compute, but some property of A5 be used here. If there is a homomorphism from A5 to S4, if it is a homomorphism, you know, kernel of this homomorphism must be a normal subgroup in A5. Okay? Every kernel of homomorphism, group homomorphism is a normal subgroup. If it is a ring homomorphism, it's an ideal. So it's a result. So it's a normal subgroup of A5. But you know, A5 is a simple group. For all, okay, A5, for all n greater than or equal to 5, alternating groups are simple. That's a result, very good result in permutation groups. So it's only normal subgroups are the trivial subgroup and the entire group. So what we have is, if there is a homomorphism, its kernel must be either the trivial group or the entire group A5. Kernel is trivial means our 5 is a 1-1 map. But this is not possible because our A5 has 60 order. S4 has 24 order. A 1-1 map from a group of order 60 to a group of order 24 is not possible. 1-1 function is not possible in between such a group. Not in between, from a group of order 60 to a group of order, smaller order. So this is not possible. Okay, so it cannot be identity. Now kernel of phi is A5 means what? All elements are in kernel, means every element is mapped to the identity. That means phi is the trivial homomorphism. So there is only one homomorphism from A5 to the trivial map is always a homomorphism. So only one homomorphism. If it is required non-trivial, the answer is 0. If it is to count the number of non-trivial homomorphism from then it is 0. But it is not mentioned non-trivial. So only trivial homomorphism between from A5 to S4. Okay. Here also you have to, I think I can conclude with the last, one more question I have. Okay. So this thing is, you can see that the second one is wrong. See, the group Zx, the ring of polynomials with coefficients from Z, integer coefficients. Okay, it cannot be isomorphic to Q plus. It's a very easy argument. You can see. Suppose there is an isomorphism from X to Q, then you can find an isomorphism. Its inverse must be an isomorphism from. You can take the reverse order. Q to Zx. Okay, suppose if there is an isomorphism from Q, we are considering to Zx, under and group isomorphism, identity element is mapped to the identity element here. So there is an element 1 here. It should be mapped to some P of X, which is non-zero. Okay. Now 1 by 2 is a member of Q. It should be mapped to an element Qx such that 2 times 1 by 2 is 1. So the image 1 by 2 should be mapped to P of X by 2. Okay. That, and for it to be a member of Zx, the coefficients of Px must be divisible by 2. Similarly, 1 by 3 is a member of Q. So the image of 1 by 3 must be P of X by 3 because it's preserve the group structure. If it is an isomorphism, if it is a homomorphism. So 1 by 3 has the image P of X by 3. For P of X by 3 to be an element of Zx, 3 must divide the coefficients of P of X, all the coefficients of P of X. In this way, you can see that every positive number, positive integer must divide the coefficients of P. Is not possible. Okay. So there cannot be an isomorphism between Zx under addition and Q under addition. This is not true. It's a countable set, union of countable union of countable numbers is countable. And Zx is ring of polynomial. Every polynomial has a finite degree. Okay, so it can be regarded as a countable union. You can count the number in that way. So it's a countable set. So this is wrong. D is wrong, and this is true. It is like this isomorphism. You can see as, I will just give the function. You can verify this. Okay, you just consider an element. I'm writing a1 plus a2 x plus x, an x to n, where ai is an integers. Every element Zx has this form. You just map this element to, you have to map into the positive rationals with multiplication, the Q with the Q plus with multiplication. This is the group, Q plus with multiplication. You just consider the prime factorization, P1 raised to A1. A1 is the coefficient, first constant. P2 raised to A2. P1 is the first prime, P2 second prime, and so on. Pn raised to An. You can see that this is an isomorphism that satisfies all the axioms for an isomorphism. So that this first one is true, C is also true. Okay, you just verify that. I am not going to the details of that proof. It's an isomorphism, and you will get, for example, if you want to get 1 by 2 as the image, 1 by 2 is a positive rational number. You have to, this is 2 raised to minus 1. So the polynomial minus 1 is not 2, 1 by 2. Okay. So if you want to get 1 by 6, it is 1 by 2 into 1 by 3. So you have to take minus 1 minus 3x. You have to take the minus 1. In that way, you can see there is a 1-to-1 correspondence between these two sets. And this function is an isomorphism, group isomorphism with this. Okay, this is the example that I mentioned in the one of the previous questions. That is, we have to look at the factor group Q over Z. Okay, so if I give a pictorial representation, it will be this. See, the idea of factor group, I think all of you know, because we are identifying the elements of Z to a single element. And what are the elements of this? We just consider the cosets G plus Z, where G belongs to Q. Okay, so every G in Q, you just add with each element of Z, so that all that elements will constitute a single coset. Okay, like this. So if we go for a condition 0, 1, 2 like this, minus, you can see that all integers are in a single coset, that is Z itself. Okay, and Z itself is the 0 element. In factor group, the identity element is the factor group in E plus H, E plus Z, that is 0 plus Z, that is Z. So all integers are come under this particular coset, and that coset is the 0 element. And if you take a real number, say R from here, here the G is rational. What is R plus Z? What is R plus Z? If this is your R, in between 0 and 1, I am taking R plus 1 will be this. R plus 2 will be in between 2 and 3. Minus 1, R plus minus 1 is this. Okay, and so on. Okay, you will get a corresponding element here. You can consider all that elements will go to a single. This is your R plus 1, R plus 2. For particular G, all the members G plus Z, all members in G plus Z belong to the single coset. Or if you take an R from somewhere else, then also you can come back to a point in. So that in this factor group, you have elements corresponding to all rational numbers in between 0 and 1. But 1 is identified as 0. Because 1 and 0 belong to same coset. So 1 plus Z is same as 0 plus Z. So you have the 0 is included here. You look at all rational points in between 0 and 1 except 1. Okay? 1 is excluded because 1 is same as Z. So you have in the group Q over Z, you have one element from each of this. Okay. So, or every element, there is a one-to-one correspondence between the rational numbers like this to Q over Z. This is the idea of the factor group. Okay, and you can see that this group has this property. Every element has finite order, and that I have not mentioned. Every element has, because Q. Every element of Q has the form. Every element in Q has the form, some A by or M by N. Both M and N are natural numbers. So if you take M by N plus Z, this coset, what is its nth power? Here the operation is addition, Q with the addition. Okay. So M by N plus M by N plus M by N, etc. N times M by N. Plus this is the coset. You apply the coset addition definition. What is N times M by N? That is M. It's an integer. So this is the identity element. Okay. That means every element has order a finite number. Okay. So this is a group of infinite order with every element has finite order. Okay. It's not mentioned here. So that this option is wrong. Contains a subgroup isomorphic to Z. A cyclic group. No element can generate a cyclic group Z. Because every element has a finite order. Okay. That is one of the points you have to mention here. Every element has finite order. Because of the structure of rational numbers. Okay. You can take some power, go to the integers. So 1 is not wrong. There is exactly one group homomorphism from Q or Z to Z is right. There is only one homomorphism. With this also you can verify if there are any homomorphism you take, this will, and because every element in Z has infinite order except identity. Okay, every element 0 except 0, all elements have infinite order. But here you have only finite order elements. So if you map the 1 plus Z into some Z here, it should be 0. Otherwise, so 1 by 2 plus Z. If you apply to 1 by 2 plus Z to some non-zero integer here, its order is 2, but this has order infinite order. Okay, so this second power tend to identity, but here we will never reach identity by taking the power. So it is not possible, only trivial homomorphism. Then every natural number n, it has an element G such that order of G is equal to, that is to just consider 1 by n plus Z. What is 1 by n plus Z? It's a member in Q over Z. Its order is n. Okay, G over Z is not cyclic, that also true. It cannot be cyclic. It is neither Zn or Z. So it is not cyclic. It is true. It is also true. Okay. This is again exam 2022 question. Okay. The same kind of questions I have listed here. This is not jam. I think one of them is not jam. One is not. Maybe my mistake. Okay. This order of 2 by 3 plus Z in Q over Z. No doubt it is 3. Only its third power give identity. Second power or first power is not identity. So that is easy part. The same question you can ask for R over Z. For R over Z, you will get the entire line segment, open line segment, semi-open, including 0 to 1. 1 excluded. Corresponding to every real number in between 0 and 1 like this, you have an element in R over Z. And so that if, as 0 and 1 are identified, you will get the units as a subset of C. The units are multiplicative group. So this group is isomorphic to that multiplicative group. The complex subgroup. Okay, so the same question you can ask about. So this is the one that I have mentioned there. Every infinite group need not have a subgroup isomorphic to Z. Okay, there are infinite groups in which every element has finite order, like this one, particular one, Q over Z. But R over Z is not like that. There are groups, subgroups isomorphic to Z. Because you would consider a irrational number R and take the coset. It will never terminate. R raised to n, R raised to n. As you raise never terminate. So you will get a cyclic group there. Infinite. Okay. So I think I stop here.
Thank you very much, Pridhimis, for engaging this session with a very nice collection of problems. Actually, for a faculty member, it is really difficult to do these type of sessions because they are not used to do with this type of problems in their regular teaching. So I am very grateful to you, Pridhimis, for being with us. Dear participants, now it is your time. You can share your comments about the session, or you can ask if you have any queries. Please introduce yourself before sharing your comments or asking any queries.
Hi, ma'am. I'm Harita from Manappuram. I'm studying in Marthoma College, Chingatra, final year PhD student. I clearly don't know what to say. It's a privilege to be in your class when you are teacher for our favorite teacher. And as you can see, he is a life changer for us. And thank you so much. As Vinod sir just now said, I have seen that it is really difficult for the faculty members when we ask doubts in the entrance questions because the approach is entirely different. And we can really you are very great in this. And a vast variety collection of questions. And you have almost said everything. Thank you so much. Really, we are really grateful to you, ma'am. Thank you so much.
Thank you, Harita. Thank you for your kind words.
Yes, Harita, thank you. Others? Yeah.
Hello, ma'am. My name is
Hi.
Abarna. I'm a graduate student from
Ah,
Trivandrum. Actually,
okay.
ma'am, today's class was very engaging, and as the questions which you gave us was totally, it actually covered all the concept of linear algebra, which is necessary for our JAM preparation. So, ma'am, thank
Abstract
you so
algebra.
much. Thank you so much for spending your valuable time with us. Thank you so much, ma'am.
Thank you, Aparna. Thank you. So anyway, happy that if you benefit it in some way, at least either for your exams or for your future studies, I'm so happy to know that.
Okay. Thank you, Aparna. Others?
Hello.
Yes. Yeah, Nishita.
Hello, Nishita.
Good noon, ma'am. Good noon, sir. Ma'am, today's session was very nice and very interesting too. All the problems you selected for us was really means every doubt is clear now. And thank you so much for this session. I'm very thankful to Vinod sir also for taking means for making them available for us. And thank you so much.
Thank you, Aparna. Thank you.
Yeah, thank you, Nishita. Others?
Sorry, Nishita. Nishita, where are you from?
Ma'am, I'm from Maharashtra.
Oh, graduate or postgraduate student?
I'm doing means TYBSc.
Means?
Third year BSc.
Third year BSc.
Okay, okay. Okay.
Thank you, Nishita.
Thank you.
Good afternoon, ma'am.
Good
afternoon, sir.
Good afternoon, Janvi.
Ma'am, this session was very good for me. I had reached slow theorems in MSc, but at this time I had forgotten, and it was revised in this session. Thank you, ma'am.
Okay, thank you, Janvi. You have completed MSc. Okay.
Yes, ma'am.
Oh, nice. So anyway, I couldn't go through the theories in detail because in such a platform it is bit difficult. Even though I was mentioning about silo theory, I was really wondering whether you are following or not. And we are not getting the exact interaction. That's why. So difficult to communicate theory part in this kind of a talk. So anyway, it is useful for you so much. Thank you so much. I'm really happy, blessed. Hi,
Thank you,
Janvi.
ma'am. Thank you, sir.
Yeah, thank you, Janvi.
Welcome.
Thank you, sir.
Yes.
Good
Hi,
afternoon,
ma'am.
sir,
Hi,
and
sir.
good afternoon.
Okay.
Yeah, what
Good
is?
afternoon,
Yeah, Asna, you continue.
Hasna, please.
Hi, ma'am. Hi, sir. I'm Hasna Shirin, a first year PG student from TMG College,
Oh,
and
yes.
it's really wonderful.
Srinath's school.
It's really wonderful session for us, and you give clear explanation for all questions that discussed today. And actually, we have an Indian exam on algebra on Tuesday.
Oh,
I think this session will really help me to write the exam. And Vinod sir, you have. I'm very thank you that you give us this free platform for us, and in this Sunday too, you spend your own times for us. Thank you.
yes, really. Vinod is really wonderful. We are also thinking so because apart from all the duties and responsibilities as a faculty member, as a father, as a husband, as the king of a house, and everything. Apart from all these things, he is finding time to spend for you, to at least time to find people. That is also very important. Find people every week. He is organizing such programs. Every week he is conducting exams. That is also very, as a teacher, I know. So
I'm a
anyway,
master's,
Vinod,
master
yes.
student. Vinod sir is our linear algebra sir, and
Okay.
in every week we met him Monday to Friday and also Sunday.
Yes. Yes, anyway, I really appreciate you, sir.
Thank you,
Thank
sir.
you, Asna. Thank you, Asna. Yes, Dharmendra, you can speak now.
Good afternoon, sir. Good afternoon, ma'am.
Hi, good
The session
afternoon.
was very nice and problems, all problems are also good problem, and Silotherm also very good explanation. We enjoy this session, and we want next sessions. Can you speak some books except Galen?
On algebra, I think.
Yeah, books.
Yeah.
Galen.
So Frale,
Galen.
John B. Frale, you are familiar with? John B. Frale.
हाँ नाम सुना है. Okay, yeah.
It's a very good, very student-friendly book. It's a very good.
Okay.
So almost all the books I have covered, I think Frale is the best one. Okay, and so many good books are there in algebra. Bourbaki, there is a series of books, the Bourbaki series. Then S. Lang. S. Lang is a little bit complicated one, but the preliminary parts are okay. But too many books are Chatterjee book on algebra. Too many good books are there on algebra.
Okay, thank you, Dharmendra.
Thank you, sir.
Yes.
Thank you, sir.
Good morning, ma'am.
Yeah. Yes, Gayatri.
Good morning, sir.
Sayanta, yes.
Sayanta.
Good morning, ma'am. Good morning, sir. Thank you, ma'am, to give such a valuable time, and I'm very good collection of questions and discussion. I'm very much happy to be a part of this session, and thank you once again, sir.
Thank you.
Very,
Thank you,
very
sir.
helpful for me.
Yeah, Sayanta, could you introduce yourself?
Sir, my name is Sayanta Kumar Kuila. I am from West Bengal. I pursued my master's from Presidency University, Kolkata.
West.
Okay,
Dharmendra was from?
I am from Kasganj, and I am doing library job in BARC Visakhapatnam. So I am living in BARC Visakhapatnam colony. That is 50 kilometers away from Vizag.
Okay, thank you, Dharmendra. Yes.
Hi, ma'am.
Hello,
Yeah.
Arya.
Yeah, yes, Arya.
So my name is Arya, and I'm from St. Joseph College, Devagiri. And first of all, thank you, ma'am, for this next section, and your explanation is very nice. Actually, I should face many difficulties